Hello grade 11s, in today's video we're going to be looking at intermolecular forces. We're going to be looking at the different types. This is super important for exams, super important for you to know for matric. So subscribe for more videos like this and let's jump right into this one. In the previous video we discussed the differences between intramolecular forces and intermolecular forces. Remember, intramolecular forces are the bonds that is within the molecule. That is not what this video is about. Intermolecular forces are between different molecules, and that is what this video is all about. Now, intermolecular forces basically deal with the attractive forces between molecules. So one molecule is attracted to another molecule. And the reason why this happens is because of charge distributions. The first thing that you need to remember is that positive and negative charges attract each other. And as you can see over here, this is a positive or a partially positive side of this molecule, and this is a partially negative side of this molecule. I'll explain and go over what that means now, but what I want you to focus on for now is negative and positive attract. And that is the basis of what makes intermolecular forces work. Okay, so it's attraction. And these forces of attraction happen because of the charges of the particles or because of the charge distribution. Let's take a look into that a little bit more closely. By the end of this video, you will know this entire table behind me. This is a nice summary, so stick around throughout the whole video to get this table, and you'll be able to explain all the different types of intermolecular forces, what it occurs between, and give me examples. The first thing that I have to remind you of, this is very important in order for you to understand intermolecular forces, is the difference between a polar molecule, which we can also call a dipole, and a non-polar molecule. Very quickly, I have videos on this in detail, so check out the links in the playlist in the description box below for that playlist. Polar molecules, they do not have an even charge distribution. So if you take a look at the molecules that I have over here, for example, HCl, if you look at the electronegativity of hydrogen and chlorine, so if you look at a periodic table, chlorine's electronegativity is 3 and hydrogen is 2.1. Chlorine has a greater electronegativity, so it has a stronger pull on the shared pair of electrons, and that makes chlorine slightly negative. You can see over here I've drawn the partially negative symbol, leaving the hydrogen partially positive. Basically what it means is the electrons lie closer to chlorine. So the charge distribution is not even. One side of the molecule, being the chlorine side, is more negative than the other side of the molecule. We call this a dipole because we can say the poles are the positive pole and the negative pole, and dipole means two poles. Okay, and this is basically my non-ideal molecular shapes, like the bent shape, like water. You can see that this end of the molecule, the oxygen end, is more negative, slightly negative. The hydrogen end is more positive. It's not an even charge distribution. Non-polar molecules, on the other hand, have an even or asymmetrical charge distribution. So if you look at iodine, for example, the difference in electronegativity here is 0. Same thing for bromine. It means that the electrons are shared evenly, even charge distribution. One side of the molecule isn't more negative or more positive than the other. And this is more like your ideal molecular shapes, like this one over here is tetrahedral. And non-polar molecules are not dipoles. They don't have two poles. They're not dipoles. So we get polar molecules, non-polar molecules. Then we also get ionic compounds. For example, NaCl. You can also think of it as sort of polar, but it's ionic. It's made up from a metal on the left-hand side of the periodic table and a non-metal right-hand side of the periodic table. We know that it's sodium ions and chloride ions. That makes up ionic. So other types of ionic compounds could be potassium permanganate or anything really that is made up of, your positive ion and your negative ion. So jumping into our first type of force on my table over here is ion-dipole. And I said it occurs between ions and polar molecules. Remember, we said polar molecules are dipoles. So ion-dipole. An example is NaCl, which is your ions, your ionic compound, dissolving in water, which is your polar molecule, your dipole. So as you know, ions can either be positive, so cations are positive, that's how I remember it. Cations are positive or positive, these ones over here, or negative, like anions, sounds like onion, makes you want to cry, anions. And these ions can get attracted to a polar molecule. Because remember, polar molecules, and I'm going to use hydrogen chloride as an example, this side of the molecule is slightly negative or partially negative. This side of the molecule is partially positive. So if I have an ion, it can get attracted to one of these sides of the molecule. So if I have a positive ion, a cation, for example, a sodium ion, it will get attracted to the chlorine. If I have a negative ion, for example, a chlorine, it'll get attracted to this side of the molecule, and that forms an ion-dipole force. And the strength of this force depends on a few things: the size of the charge, so you get bigger charges and smaller charges, how strong the dipole is, so how big the difference in electronegativity is. If it has a big difference in electronegativity, it means the one side of the molecule is very positive, the other side of the molecule is very negative, and also the distance between the ion and the dipole. And just by the way, ion-dipole forces, this is the reason why ionic compounds can dissolve in polar solvents like water. And it's because of that ion-dipole attraction. So you can take a look at this photo over here. It basically shows you how the sodium ion gets surrounded by the electronegative or the more negative part of the water molecule. And similar thing happens with the chloride ion. The second type of force is called an ion-induced dipole. So what makes us different from the first is the word induced, and I'll explain what that means now. But ion-induced dipole takes place between an ion or an ionic substance, that's where the ion comes from, and a non-polar molecule, which is where induced dipole comes from. As soon as you see dipole, just dipole, then think polar molecule. If you see induced dipole, I want you to think non-polar molecule. So let me explain what induced dipole means. Let's pretend we have a bromine molecule. So that would be Br2. If you do the difference in electronegativity, you take the electronegativity of bromine is 2.8 minus 2.8, you get 0. You know immediately it's a non-polar molecule. That means that when it shares its electron pair, so as you know, it shares one pair of electrons here, they lie exactly in between the two bromine molecules. One bromine molecule doesn't have a greater pull on that shared electron pair than the other. It lies in between. It's an even charge distribution. Now, what happens when an ion comes along? So let's pretend it's a positive ion, such as the sodium ion. Once again, it could be any positive ion. So like a magnesium ion or iron or anything really, as long as it's an ion and it comes along. It doesn't have to be positive, it can be negative as well. Now, as this ion approaches the bromine molecule, what I want you to remember as of now is that there's an even charge distribution. So think of it as the electrons are evenly distributed around the molecule. But as this sodium ion moves closer to the bromine ion, what do you know about positives and negatives? They attract. So what ends up happening is all these little negative electrons temporarily get attracted to the sodium ion. And look at what happens. This side of the molecule becomes partially negative, and this side of the molecule becomes partially positive. This side becomes partially negative because all the electrons have kind of rushed that side because it's attracted to the ion, leaving this side over here less negative because there's no more electrons or less electrons, therefore partially positive. So what we've done is we've basically created a temporary dipole where the one side of the molecule is more negative, the other side is more positive. It has been induced. The word induced means it has been created, basically. It's been created or brought upon. So because of the sodium ion over here, that created a dipole in my nonpolar molecule, but it's temporary. If the sodium ion moves away, then the electrons will redistribute and it'll become completely nonpolar again with the even charge distribution. So here's a nice summary of what happens, exactly as I've mentioned, and it is temporary. If we remove the ion, the electrons will rearrange themselves until the charge is even once more. So it's basically just because of the presence of the ion that the electrons get distorted. So just remember, when you see ion-induced dipole, it's with an ion, and induced dipole means non-polar. As soon as you see the word induced, I want you to think non-polar. Our next one is called dipole-dipole. And as we've mentioned already, a dipole is a polar molecule. So dipole means between polar molecule and polar molecule. My example here is water and alcohol. So I've got over here that a dipole-dipole force is an attraction between polar molecules. They have permanent dipoles of the same substance or different substances. So in my picture over here, I have HCl attracted to HCl. So in this case, it's same substance with same substance. But like I said, it could be alcohol and water, or HCl and water, or any two polar molecules. So again, basically it is the positive side of this dipole will be attracted to the negative side of this one. The negative side of this polar molecule or this dipole will be attracted to the positive side of this one. Now, under dipole-dipole, you get a special type of dipole-dipole. This one, so important. It's called hydrogen bonding. Now, don't let this mess with your brain. It's called hydrogen bonding, but it's not a bond. Okay, I know it's weird. I don't know why they called it hydrogen bonding, but it's not a bond. It's called hydrogen bonding, but it is still an intermolecular force. Intermolecular, meaning that it occurs between molecules. And how do you know if it's going to be a normal dipole-dipole or a special type, which is hydrogen bonds? So it says here, hydrogen bond, a force of attraction between a hydrogen atom bonded either to an oxygen, nitrogen, or fluorine in a molecule. And basically, this just happens. It's got to do with the fact that there is a lone pair in the molecule, and also because of the big difference in electronegativity. It basically just creates a molecule that is very, very polar. So for example, water is a very, very polar molecule. Also because of the lone pairs on the oxygen. It means that this side of the water is very, very negative, and the H side of the molecule is very, very positive. So because this side is very, very negative, it gets very strongly attracted to this side of this water molecule, which is very, very positive. I hope that makes sense. So it's not like this is just like a normal kind of negative and this is like kind of positive, so they kind of attract each other. This is very negative. And this is very positive. So they form a strong attraction to one another. And as I said, this only occurs in molecules where you have the hydrogen bonded either to a nitrogen, oxygen, or fluorine. So how I remember it is I call it H-NOF. That's how I remember it. It has to be a hydrogen with either a nitrogen, hydrogen with oxygen, or hydrogen with a fluorine. So water fits this case because it is a hydrogen, tick, and an oxygen, tick. So hydrogen and oxygen. Something else that could fit this situation is NH3 because, again, it's hydrogen with nitrogen. Something that does not fit hydrogen bonding is HCl because it is hydrogen, but this is not nitrogen, oxygen, or fluorine. It's chlorine. So that's not hydrogen bonding. HCl and HCl would be normal dipole-dipole forces. So here is a really good explanation of hydrogen bonding. And what is super important for you to know is that hydrogen bonding is one of the strongest types of intermolecular forces. Very, very strong. So if you're comparing hydrogen bonding to normal dipole-dipole, hydrogen bonding wins. If you're comparing hydrogen bonding to something that exists with non-polar molecules, which we'll discuss in a bit, they're called London forces, hydrogen bonding wins. Okay, very important. It is an intermolecular force, despite its name, and it's got to do with the large difference in electronegativities. That is why hydrogen bonding is so strong. Some examples of substances that have hydrogen bonding would be water molecules because of the O and the H, alcohol molecules because they also have an O and an H, something called glycerine or glycerol because they also have an O and an H. So you need to be on the lookout for anything where a H is bonded with a nitrogen, oxygen, or fluorine. So just take note, I haven't included hydrogen bonding in this table because it falls under dipole-dipole, but just be aware of it. My next one is dipole-induced dipole. Now, I hope you remember, when you see dipole, think polar molecule. When you see induced dipole, think non-polar molecule. So dipole, induced dipole, polar and non-polar. So what happens here is something very similar to what we described before. I'm going to use bromine again, Br2. It's a non-polar molecule, as we mentioned before. Shared electron pair lies directly in the middle, even charge distribution. Think about it. All these little negatives I'm drawing, even charge distribution. But then a polar substance like water comes along. And as you remember, or as you should know, we have the oxygen and the hydrogens like this. The oxygen is partially negative, the hydrogen's partially positive. I've done this in previous videos, why that's the case. As this approaches the bromine, what do you know about negatives and negatives? They repel. So these electrons over here will be repelled from the oxygen side of the molecule, and they'll move here. That will leave this side of the molecule partially negative and this side of the molecule partially positive. So again, we have induced a dipole. We have taken something that is non-polar, that is even charge distribution, and we've induced, or we've created, a dipole. And then they get attracted to each other. That is where the intermolecular force comes in, called dipole-induced dipole. So there's an explanation of that if you need it. And then our last one. Now, our last one is called induced dipole, induced dipole. And if you've been following what I've been saying, induced dipole means non-polar. So induced dipole means non-polar, non-polar. And we far more often than not refer to this as London forces. And if you remember what I said earlier, I said hydrogen bonding is the strongest type, dipole-dipole is weaker than hydrogen bonding, and then the weakest type of intermolecular forces that we have are called London forces, and they actually exist between all molecules. Now, I know I say here between non-polar and non-polar, that is true, but they can also exist between all other types of molecules as well. So if I have water and water, yes, there's hydrogen bonding there, but there's also London forces. Okay, but London, non-polar molecules, they only have London forces. Okay, now let me explain what this means. So this is a very long explanation, but basically, if you have two non-polar molecules, and again, I'm going to use bromine, as you know, they have an even charge distribution. So the little electrons are distributed evenly around them. But what actually happens is that over time, as time goes on, the electrons kind of move and fluctuate. So any moment in time, so say 1 second, they're all evenly distributed. The next second, this side of the molecule can have more electrons than this side, leaving this side more negative and this side more positive, but just for a moment in time. But when that happens, another little molecule comes along, and let's say it's this bromine. And initially, all of their electrons are evenly distributed. But because for a moment in time, that initial bromine has a side that is more positive, it quickly attracts all the electrons of the next bromine molecule, making this side more negative and this side more positive. And it creates almost like a chain reaction. All you need to know, you don't need to know that in depth. So if you were like, ma'am, I don't get what you were saying, it's okay. Just remember that it is a temporary situation. So it's a non-polar molecule, another non-polar molecule, and for a single moment in time, they become little mini dipoles. But then they go back to non-polar. And it's always between a non-polar molecule and a non-polar molecule. And just remember, I said that all molecules have London forces between their particles. So even if they have hydrogen bonding or dipole-dipole, they have that plus London forces. It's very important that you say and London forces in your exam, because if you don't, we can mark you down. And as I've mentioned already, hydrogen bonding is the strongest type of the intermolecular forces that we deal with most commonly. So hydrogen bonding, dipole-dipole, and London forces, those are the three that pop up most often in your tests and exams, even up to matric. So hydrogen bonding is the strongest out of those three, then normal dipole-dipole, then London forces. Here are some important things to note as well regarding intermolecular forces. Very, very, very important. And now I want to give you a few examples like we can ask you in your practicals or in your test. So let's see if you can name the correct intermolecular force. What type of intermolecular force occurs between molecules of water and bromine? So what you're going to have to do is determine water, is that a polar molecule or is it a non-polar molecule? I hope you know by now that water is a polar molecule, and it also actually has that H-NOF bonding. However, if it was water and water, then it would be hydrogen bonding. So even though water has hydrogen and oxygen, it doesn't mean hydrogen bonding, okay? It's if it's water and water. So two things that have H-NOF bonding, then it'll be hydrogen bonding, okay? Just keep that in mind. So we've got water is a polar molecule, and bromine, I've been mentioning in this video that it is non-polar. So I hope you know that the intermolecular force between these two, remember, as soon as you see polar, I want you to think dipole. So you're going to write dipole, then you're going to do a dash. Non-polar, I want you to think induced dipole. So the force that exists between molecules of water and bromine, dipole, induced dipole. So that would be like if you have a little water molecule and you have a little bromine molecule. That would be the little forces that exist between them. What about water and alcohol? Now, remember we said water is a polar molecule. Alcohol is a polar molecule. So you might be thinking polar and polar, dipole, dipole. That is correct. It is dipole, dipole forces. However, remember water contains some of our H-NOF bonding. There's hydrogen bonded to oxygen. And I said your alcohols are polar molecules that contain an oxygen and hydrogen bond. So again, H-NOF bonding, hydrogen and oxygen. So we have two substances that have hydrogen bonded to oxygen, hydrogen bonded to oxygen. So when they come together, it actually forms hydrogen bonding, the special type of intermolecular force. Hydrogen bonding, special type of dipole-dipole. Remember, it would be hydrogen bonding and London forces. Remember, everything is London forces. Let's do two more. What about carbonate ions and water molecules? Again, at this point, you should know that water is polar and carbonate ions, those are ions. That's ionic. So ion, and what do we call polar molecules? Dipole. So ion dipole forces. Last one, what type of intermolecular forces occur between molecules of bromine? So they mean one bromine with another bromine. That's what they mean. One bromine with another bromine. So Br and Br. That would be bromine is nonpolar. This bromine is nonpolar. So what did we say about nonpolar? Induced dipole, or London forces. There we go. I hope that this video has been helpful. Let's do one more little flashback to my summary table. There we go. Please, please, please study this because this is going to be very important when dealing with physical properties like boiling point, melting point, all those things. So I hope to see you in other videos where I go over those physical properties. Remember to check out the links in the description box below for those videos, and I'll see you in another video very soon. Bye, everyone.